Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 896, Monotonic Array. There's a variant that transforms this easy problem into at least a medium problem. But anyway, let's get started. Given an integer array named nums, return true if the given array is monotonic or false otherwise. You may naturally ask, what is a monotonic array? Well, it's an array that is monotonic if it is either monotone increasing or monotone decreasing. That didn't answer anything, and I'll tell you right now, neither does this paragraph, or at least very well. Let's just look at a few examples to figure it out. Take exhibit A. If we're given this input array, then this would be a visualized version of it, presented as a line graph. We'd return true, and as to why, it's because this is a monotonic sequence, specifically a monotonic increasing sequence. Easy enough. What about this? We'd also return true because inversely we have a monotonically decreasing sequence. Putting the two together would get us something like this. It has an incline and then a decline. We'd return false because as per the requirements, we only return true if the array is entirely increasing or decreasing, but not both. All right, there's two more possibilities. Let's check them out. This one is still considered monotonically decreasing, and thus we arrive at the full definition of a monotonically decreasing sequence. It's a sequence of values that remain the same or decrease in value. We return true. We'd also return true here because we oppositely have a monotonically increasing sequence, one whose value remain the same, or they increase in value. This does imply that if the entire array was flat like this one, then it'd also be a monotone array. But anyway, back to our example. The moment we have a decline, then we'd have no choice but to return false. Remember, we cannot have both types of monotone arrays. As to how we knew we had a decline, we can obviously compare this value with the one before and observe a decrease in value. That sounded programmatically accurate. I am a developer, and I do like it when things are explained within the confines of programming rules and overall opinion. So let's do one more example and in a way, pull back the curtain of each data value, one by one. Maybe then it'll give us some intuition on the problem solving. Okay, here's our first data value. Let's do what we did before and compare it with the number before it. And get an out of bounds error. Not ideal. To avoid this, it'd be logical to start on the second value, right here, where here we note a flat sequence. So for all we know, we could still have a monotonically increasing sequence, correct? Let's put that in a Boolean variable called isInc. Inc for increasing because I'm lazy, and default it to true. Extending this idea, we also still have a monotonically decreasing sequence because it's one that decreases or remains constant. We'll likewise initialize a isDec, dec for decreasing, Boolean variable, also set to true. All right, let's reveal the next value, and okay, we have another duplicate data point. Comparing it with the one before leads us to note their equal values. So there's nothing to do. We still retain the possibility of a monotonically increasing or decreasing sequence. If we unveil another value, we see our first jump upwards, a characteristic of a monotonically increasing sequence. We ask a pivotal question, do our Booleans still hold true? Well, for is increasing, yes, but I can't say the same for is decreasing. The logic is simple. If we encounter an increasing sequence, then our only hope to return true in our overall function is to have a monotonically increasing array. That is, we're hoping that the remaining data points remain constant and or increasing. Maybe something like this. But on the flip side, this signifies we no longer have a decreasing sequence. Is decreasing should be set to false. And FYI, the vice versa is true, that if we ever have a decline, then we cannot have an incline array. We'd oppositely be setting is increasing to false. Moving on though, we have a flat sequence. That's fine. That doesn't really affect our Boolean siblings here. Revealing another data point and moving onwards, we continue our upwards trajectory. This number is greater in value than the one before. Logically, we still have a monotonically increasing array, not a decreasing one. So remember, we'll do what we did before and set our is decreasing from false to false. So nothing really changes. We move on to the next iteration, where it's the same deal. We update is decreasing from false to false. Great. Up next, we have an unsuspected decline. This ruins our chances of achieving a monotonically increasing sequence. We'll have to sadly update is increasing to false. Now, since we can't achieve either one, we're finished, right? Do we stop our algorithm prematurely and return false? What did I have for lunch yesterday? Why am I asking so many questions? But rest assured, the answer is yes. If on any given iteration, if both of our Booleans are false, we'll just return false. And that would be our answer. And if we reveal the rest of our array, okay, thank goodness we stopped early. I wasn't about to do that for another 30 iterations. The time complexity is big O(n) because of a single for loop left to right for each data point. And the space complexity is big O(1) since we only used 2 Boolean variables. The number of variables don't change if we're given an array of 1, 10, or a billion values. Alrighty, the code does mimic the logic one for one. Let's do it. Let's spin up the 2 Booleans we know and love, is inc and defaulted to true, and is decreasing, also set to true. Afterwards, we'll begin our for loop with pointer I from index 1, not 0. We want to avoid our code from imploding, remember, to the rest of the array. On each iteration, we'll see if we have an incline in value or not, and we know that if the current value is greater than the value before it. If so, this means we cannot achieve a monotonically decreasing sequence anymore. Let's reflect that in is decreasing. Set to false. As for the other case, if we have a decreasing sequence, so if the current value is lower than the one before it, then we'll oppositely set is increasing to false. And yes, there's the case where we have a flat sequence, but in that case, as we saw, there's no logic to execute. But let's introduce our slight optimization, that if both Booleans are false, then we'll break out early and return false. If we make it out of this for loop alive, then we either have a monotone increasing array or a decreasing array. Let's return true. Sweet, that's the code. Brace yourselves, it's time for a tough variant. Alright, the variant really puts things into overdrive, launching the original LeetCode problem into the medium territory. Let's do a quick read. Given an array named nums, return the count of strictly increasing, strictly decreasing, and unchanging sequences within the array. Short and sweet, very nice. Taking a look at our example here, we'd count 1, 2, 3, 4, 5, and 6 sequences, 2 of which are increasing, 2 decreasing, and 2 unchanging, or how we refer to them, flat sequences. 6 is our answer, that's what we return. Please note, we shouldn't count subarrays. So for something like this, we only count it once, not 3 times. In my opinion, this is one of those problems where you think through the workflow and scribble down pseudocode as it vaguely relates to for loops, booleans, and if statements. I'll be showing my thought process. I'm hoping it's not too chaotic. Let's do it. Okay, so looking at our omega example here, we know we want to be on the lookout for strictly increasing and decreasing sequences. So why not a direction variable to track that? Perhaps a boolean where true denotes an increasing sequence and false a decreasing one. So what do I default this to? I mean, before we even start our algorithm, we don't really have a direction at all. I'd ideally like to represent this weird initial state, so this is what I'll propose. To be able to introduce a third state, a boolean just won't cut it. So why not an integer variable, where 1 can denote an incline, 0 a decline, and -1 for the initial state that we can default to. In our pseudocode, let's just note that initialization down. Great. What else do we need? Most likely a count variable of some sort to capture the number of sequences. Sure, let's add that too. Oh, and return it before I forget. For the main logic, like before, we'll loop left to right, and on each iteration, we can look one element back and observe an increase or decrease. So on the first iteration, we look back one number and encounter an out-of-bounds error. That's right, let's start our loop on the first index, not the 0th. Let's represent this in our pseudocode. And while we're here in the pseudocode, let's capture some logic we briefly described and actually had in the OG implementation. An if statement to see if we have an increasing sequence, so if the current number is higher than the one before. Let's not forget the other possibility. If the number is lower than the one before, then we oppositely have ourselves a decreasing sequence. Okay, now we're ready. We look back one, and we neither have an increasing or decreasing sequence. Turns out we have a flat sequence. I remember now that is a thing, where you go from a value to a duplicate value. Thus, it kind of resembles flat terrain. This must be included in our count. As the how, I'm not sure what to do. I'm panicking. Let's just introduce a boolean called isFlat. That in this case will default to false, but because of this current iteration, we'll set it to true. We'll hold off on any further logic because procrastination. Don't act like you've never done it before. Let's reflect this in our diligent notes. We'll default it to false, yes, but also introduce another if statement branch for the last possible case, the case of flat terrain. If this gets executed, we'll flip the boolean to true. Very logical. Again, we're not doing much with it, but we'll keep it in the back of our heads. We'll address it as necessary. We'll move on to the next iteration, where we once again neither have an increasing or decreasing sequence. It's flat. I suppose all we do is update our flat boolean from true to true. Onwards and upwards, we increment our I pointer where we're finally making some ground. We realize we have an increasing sequence on our hands. This value is greater than the one before. Sounds like a trivial nested if statement to me. That in our pseudocode, if the current direction is the initial state of -1 and we're increasing, duh. Let's increment count. You'll notice I snuck in another conditional where we increment the count if the direction is also 0. Getting the obvious out of the way, I do foresee a standard situation where we come from a decreasing sequence. Or in other words, when the direction is an integer of 0. But anywho, as per our new code instructions, we'll add 1 to our count here. This increasing sequence is now included. We're sadly not done with this iteration just yet. Recall moments ago I was procrastinating on counting flat sequences. Well, here's an opportunity to capture it. That if we don't do it here, I don't know when we would. So if we encounter an increasing or decreasing sequence, then you could possibly come from a flat sequence. We want to count both of these. Let's update our count variable to 2 for those two sequences. Another thing, let's update our isFlat variable to false, resetting it until we see another flat sequence, which, spoiler alert, that'll be the next iteration. In our handy dandy notebook, we'll write down exactly that if we additionally came from a flat terrain, we'll do those two things, flip the boolean and increment count. Are we done with this iteration? Am I forgetting anything else? Yes, I am. We're on an incline, so let's not forget to reflect that in our direction integer, 2, 1. Sweet. That was a long but productive iteration at that. We ironed out a lot of the workflow and overall possibilities. Moving along, in our example, we move our index, look at the number before, realize it's a flat sequence. Acting on this, we'll set our isFlat boolean to true and do nothing else. On the new iteration, we clearly have another ascending climb, but unfortunately, as per our pseudocode, things won't work out very nicely. We came from a flat sequence yet again, so sure, at least we increment the count variable once because of this. But the issue is, we won't capture the increasing sequence like we did before. And it's true, inspecting this if statement, we didn't come from a decreasing direction or an unknown one, did we? Or at least according to our direction variable, we didn't. But anyway, to make this work and count this sequence, let's think on it a little bit. If we examine the only other time we had an increasing sequence, then remember, we didn't yet have a direction of 1 to represent an incline. We only updated it after the fact, after our if statement checks, right here. Instead, we had a direction of -1. That's where we came from. The jank logic was, we'd increment our count variable if we came from this unknown state. Similarly, here, we're coming from a flat sequence, this Boolean of true, but the difference is we have a direction of 1 that we're coming from. So let's jank our workflow a bit more to say that if we ever have these two values, then we can increment our count 2 times. Once for the increase and once for the flat terrain that led into it. Sure, why not? 4 for the 1, 2, 3, 4. Lastly, don't forget to update the is flat Boolean to false, since we already counted the flat sequence. Nice job. That was a bulky amount of logic. Great work. This pseudocode is starting to remind me of the messy code bases I used to work on. Moving on, we shift our eye where we have a continued increasing sequence. Nothing changes but updating our direction from 1 to 1. That makes sense, and that's because we're still on an incline. Thank goodness our pseudocode doesn't double count. We only increment count once for this sequence. And on that note, the same deal for the next iteration. All we'll have to do is change the direction from 1 to 1. And you know what? I'll make a bold claim right now. I'm confident we've covered every case possible for an increasing sequence. That 1, we could be coming from a flat sequence with a direction of -1. 2, from a flat sequence in a direction of 1. And 3, I didn't really get to show this part yet, but if we came from a decreasing sequence, which would be a direction of 0, we'd also increment our count. Sounds good. I'm practically going to copy and paste the same logic for decreasing sequences, with minor changes, of course. And with that, let's go through the rest of our example to see if everything remains functional. I'm going to zoom through it, so feel free to pause and double check my work with the pseudocode. On the next iteration, we have a descending sequence, and we know that because our direction is 1. 1 for increasing. To capture this, we'll increment our counts to 5, update our current direction to be 0 to denote the downwardness, and then move onwards. After we look back, observe a flat sequence, all we'll do is update our is flat Boolean. Sweet. Next up, we have another descent, but we'd like to capture the flat sequence we just came from, as well as the descending sequence itself. So we'll do 2 things. We'll add 2 to our count to get 7, and flip the is flat Boolean to false. We'll also technically update our direction to be the same value of 0. We're still on the downwards trajectory. On the last iteration, how exciting, we find ourselves with more flat terrain. We know what to do at this point. Turn is flat to true, and we're done. We have a total of 7 sequences. The 1, 2, 3, 4, 5, 6, 7, and 8. I see the problem. We awkwardly counted flat terrain only when we encounter an incline or decline. But the issue is, if our line graph ends with flat terrain, we'd never count it. There's clearly no following increase or decreasing value. Sounds like a job for an afterthought if statement. That after our loop, if our is flat Boolean is true, we'll increment the count one last time. And there we go. We captured the last one, and we're officially finished. Overall, our outlined workflow covers everything. It's a bit spaghetti, but that's okay. No one's going to notice. The time complexity is big O(n) because of a singular for loop, and the space complexity is big O(1) since we only used fixed variables. Alrighty, we have some nice pseudocode to mimic. Implementation should be easy. Let's start. Okay, what were the 3 variables we needed? It was a direction that started in the unknown state of -1. A count integer variable defaulted to 0, and let's return that before I forget. and a is flat boolean set to false at first. We'll begin our for loop where we'll carefully start at the first index. Let's write down the skeleton of the algorithm for the 3 possible sequences we can achieve. What if the current value is higher than the one before? If so, we must have an ascending climb. What if the current value is lower than the one before? Oppositely, we'd have a descending fall. If we have neither of these if statements, then we have 2 duplicate values in a row. This is the simplest if statement. Remember, all we do is set is flat to true. Okay, filling out the code for the increasing sequence first. If we came from a descending or an unknown direction, we'll increment our count variable. If we came from a flat terrain and an increasing sequence, we'd like to count both. Let's do that and then set is flat to false. One more if statement. If we only came from a flat sequence, a flat terrain, we'll similarly increment count and then flip the is flat boolean. Last thing to do in this huge code block, since we're on an increasing sequence, let's reflect that in our direction variable. We'll set it to the 1. After, we'll write parallel code for declining values. Let me type as fast as I can. Alright, after our for loop, recall that if we end in flat terrain, we can increment the count one last time. Okay, and that's the code. I'm very proud of this. I consider it near perfect, but if I did a PR review, I would just leave a comment saying, get good at Python. But other than that, there's nothing at I don't like the code, it's smelly. A direction integer variable to represent 3 states is not very readable or intentional. Noob cake. Why not an enum? Okay, fair. I mean, in an interview, you only have so much time. Bro, dude, there's too much cognitive complexity, too many if statements, lots of duplicate code too. I mean, yeah, I don't typically extract functionality unless it's duplicated at least 3 times. Thank you for the video, Minmer. Yes, you're welcome. The if statements are confusing, at least add comments. Alright, fine. Let's see how we can refactor the code. First up, let's knock out some low-hanging fruit and make our code a bit more readable. Instead of an integer for our direction variable, let's opt for an enum. We'll call the class direction because that makes sense to me. It'll have unknown for the initial -1 state, decreasing of the familiar 0, increasing of 1. Fantastic. With this, let's propagate this enum throughout our code. That instead of -1, we'll initialize it to a direction of unknown and include this in our if statement checks. So far, the functionality remains the same, mind you. After this, we'll then replace all the increasing directions of 1 with our shiny new enum. Here, here, and here. Same deal for the decreasing sequences. Okay, a solid win. But the next one might throw our code for a loop. People were complaining that the code is too long and there's too much redundancy. Specifically, there are too many if statements. Very fair. Let me explain the root of the problem. We treated a flat terrain differently than we did with increasing or decreasing sequences. But isn't flat also a direction? I suppose it's unchanging, but still a direction nevertheless. It'd make our code more cohesive and sensical if we included this direction into our enum. Switching to the code, this means we could have a flat field to a value of 2, sure. This further means we can replace our is flat boolean with this new value and removing references where possible. Here, we'll change this boolean check to use our direction variable and removing these silly boolean flips. We'll do the same thing here as well. Remove is flat. And here, From here, because we introduce a flat direction, we can actually benefit from a lot more clean code. Let's spell out these implications. That if we consider this a direction, then we don't need separate logic to awkwardly count these flat sequences after the fact when we encounter an increasing sequence, for example. Instead, we can count it the moment we observe a flat terrain. So, in the else branch, if we have a flat sequence, but our direction doesn't reflect that, then let's immediately flip that boolean to flat and increment our count. And if we have this logic in place, then there's no need for redundant logic to check for flat sequences in the case of increasing or decreasing sequences. So yep, let's remove these excessive if statements. Furthermore, we don't need this if statement anymore. We check for unchanging sequences immediately. Let me show you that if you have something like this, on the first iteration, we check the element before, realize we have a flat terrain, execute this else statement to increment our count correctly, increment our I pointer, and we are done. We have the 1 for the 1. Cool, it works out. But hold on, let's not be overzealous with removing anything related to flat directions. If we had an example like this, then to count this decline, we'd technically be coming from a flat sequence, right? Same goes for inclines. Thus, let's update our if statements. We'll update line 13 to say that upon increasing sequences, we can still come from flat terrain. Oppositely, same deal for descents. You may have noticed I overwrote the fact that we can come from an unknown state. Does that mean we've eliminated this possibility from happening? As always, let me show you with a picture. That to answer this, but also to refresh our memory, in our legacy code, if we were given something like this, then remember, when we encountered our very first increasing sequence, or decreasing for that matter, then in actuality, we wouldn't be coming from a flat sequence, because this wasn't in our enum, but rather from an unknown state of -1. But now, with our new code, if we consider the flat sequence immediately, then we know we're coming from it. Problem solved, right? Almost. This is true, except for the very first iteration. Specifically, in the case that we have an increasing or decreasing sequence. Do you see how we'd still be coming from an unknown state? This is because it takes at least one iteration to realize that we're in the flat direction, like we see here. But in the case where we're increasing or decreasing immediately, then we're still not coming from any real state at all. It's an unknown state. Therefore, to count these situations and add 1 to our count, but not in this situation, we'll update our logic as follows. Our count will start on 1 if the second element is not equal to the very first one. Therefore, it's strictly increasing or decreasing. Otherwise, if it's not, if it's flat, we start with the ordinary 0. And there we go. Our code is simplified. As a last note, I know our constraints say that our input list will always have at least 2 elements. But what if your interviewer tries to screw you over? Well, line 10 would blow up. So let's handle this in an if statement. That if the length of our nums is 0, then we'll return 0. 0 for 0 sequences. The fun doesn't stop there. What if we're given exactly 1 element? Let's handle it manually by including it in our if statement. A single data point isn't considered a sequence. Great work today. I hope that all made sense. I wish you luck on your interviews. Easy LeetCode problems aren't always easy, and if you learned something today, please make sure you like, comment, and subscribe. Thanks.